Hello everyone, in this video I will talk about the anisotropic nature of wood. Wood is a very well-known example of anisotropic material. For anisotropic materials, their properties depend on the direction in which they are measured. In contrast, isotropic material has the same properties in every direction. In the previous classes, most of the materials I mentioned are isotropic materials, including cement, concrete, aggregates, asphalt, etc. But one example of anisotropic material is cold-formed steel sheets. These steel sheets are formed by squeezing thick sections of steel between heavy rollers. This flattens and stretches its grain structure, and you can see the grains before they go through heavy rollers. This is the schematic illustration. This is the real picture. And here are the pictures for the grains after they go through heavy rollers. So you can see the grains are elongated in this direction. This is the schematic illustration. As a result, the material becomes anisotropic. Its properties differ between the direction it was rolled in and each of the two transverse directions. So, for example, if you perform a tension test in this direction and in this direction, the Young's modulus, for example, in the two directions are different. So that's the most significant features of anisotropic materials. That is, the physical properties and mechanical properties are different in different directions, such as shrinkage, stiffness, and strength, etc. Orthotropic material is a subset of anisotropic material because their properties change when measured from different directions. In material science and solid mechanics, an orthotropic material is defined to be one in which there are three mutually perpendicular planes of symmetry. And as shown in this figure, you can see wood is a well-known example of orthotropic material. In wood, you can find three mutually perpendicular directions at each point in which the properties are different. These are the axial direction along the grain, the radial direction, and the circumferential direction. The radial direction and the circumferential directions are perpendicular to the grain. So from this figure, you can see this is the longitudinal direction or the axial direction, which is parallel to the grain. And these two directions, tangential direction and the radial direction, are perpendicular to the grain. So here you can see this is the growth rains here, and this is the grains. So the parallel to the grain, we get the axial direction or longitudinal direction L, and the T direction and R direction are both perpendicular to the grains. So the T direction, perpendicular to the grain and tangential to the growth rains. So this direction is called the tangential direction or circumferential direction. And this direction is also perpendicular to the grain, but it's normal to the growth rains or cross the growth rains. So this direction is called the radial direction. So wood has different mechanical properties and physical properties in these three different directions. The typical stress strain curve of wood specimen is linear up to a certain limit, and followed by a small nonlinear curve, after which failure occurs. The Young's modulus of wood is the slope of the linear portion on the stress strain curve. The stress strain relationship of wood typically varies between different species of trees and even within one species. It's affected by variation in moisture content and specific gravity. We will talk about moisture content in greater details later. Since wood is anisotropic, different stress strain curves will be obtained in different directions, and the Young's modulus along different directions are typically different. So the Young's modulus along the longitudinal direction, radial direction, and the tangential directions are different. Due to the orthotropic nature of wood, we normally perform mechanical tests on wood samples in two different directions. One is parallel to the grain, which is the longitudinal direction, and the other one is perpendicular to the grain, either in the radial direction or in the tangential direction. So these are the typical mechanical tests we perform on wood samples. It includes tension test parallel to the grain, tension test perpendicular to the grain, compression test parallel to the grain, compression test perpendicular to the grain, and Janka hardness test perpendicular to the grain, Janka hardness test parallel to the grain. And finally, the binding test, which is also called the flexural test. It includes 3-point binding and 4-point binding tests performed on wood samples. In the learning module, I uploaded several YouTube videos on the mechanical tests performed on wood samples. Each video is only 1 minute or 2 minutes long. So I suggest you to spend some time watching those videos to get a rough idea about how the mechanical tests are performed. It includes a flexural test on wood when the sample doesn't have defects, and also flexural test on wood when the sample has defect. Also, it includes compression test on wood parallel to the grain and perpendicular to the grain. It also includes a video on the Janka hardness test performed on wood specimens. This figure shows the density, moisture content, and Young's modulus for some typical timber specimens, including balsa, walnut, and ash, etc. So you can see the Young's modulus is different in different directions. So this is the Young's modulus in longitudinal direction, this is the Young's modulus in radial direction, and this is the Young's modulus in tangential direction. So in 3 different directions, we get 3 different values for Young's modulus.